Today's lesson is going to be about inequalities related to triangles. We'll start out with inequalities with one triangle, and then we'll do inequalities relating to triangles. There are some investigations, and I would like you to go ahead and do those, so you will need some supplies. If you don't have a packet with compass, straight edge, and ruler, go get one. Remember, you can pause this presentation so that you can get notes down and give yourself time to do examples. To look at the first relationship, we're going to explore the lengths of the sides and how those relate to the size of the angles. So it says the positions of the longest and shortest sides of a triangle are related to the positions of the largest and smallest angles. So I need you to try this in at least one triangle. Draw a large scalene triangle. Remember, scalene means no sides congruent. So try and make it a random type of triangle. It doesn't matter if it's acute, right, or obtuse, but try and make all the sides a different length. Take time to do that, and then it says measure all the angles, measure all the sides, put your measurements right on the diagram, on the sides and in the angles so you know where they really are. So pause and do the investigation. Now as you look at your diagram, look to see where is the smallest angle and where is the shortest side. You might notice that they're across the triangle from each other. Where's the largest angle? Where's the longest side? You notice that they're across from each other? We have the relationship that if you compare two sides of a triangle, the larger angle is going to be opposite or across from the longer side. As I was leading you, we might say the shortest side is always across from the smallest angle, the medium-sized side is across from the medium-sized angle, and the longest side is across from the largest angle, which is true. The theorem kind of breaks it down into just comparing two at a time so we can do a less than or a greater than relationship. So that first hypothesis, if two sides of a triangle are not congruent. So in other words, if AB is bigger than BC, then the conclusion would be that angle C is going to be bigger than angle A. Notice I did not make those isosceles. It's a less than or greater than type of relationship. So the original theorem starts with the side lengths being known. The converse starts with the angles being known. If two angles of a triangle are not congruent, then the longer side is opposite the larger angle. So according to what it says in the hypothesis, angle Z is bigger than angle Y. So in the conclusion, XY, which is the segment across from angle Z, that side is going to be longer than the side across from angle Y, which was XZ. So again, the idea that the longer side is opposite of the larger angle. Pause if you didn't get your notes and examples done. Okay, it says write the angles in order from smallest to largest. So notice I did not give you any angle measurements. I gave you the side lengths. But use the theorem idea to help you figure out, well, based upon those sides, what angle is going to be the smallest, medium, and then largest. Okay, the answer to that one, the shortest side was opposite of angle F, and then the longest side was opposite of angle G. So in order, they would go angle F, angle H, angle G. Now I gave you a couple angle measurements. I didn't give you the third one. You'll have to figure out what that is. And then you can put the sides in order, shortest to longest. Pause and work the problem. Okay, that last angle was 48 degrees. So then across from the smallest angle will be the shortest side, then go to the medium, and then to the longest. Try again. And then starting with angles. Put the sides in order. Okay, next idea. A triangle is formed by 3 segments, but not every set of 3 segments can form a triangle. Why not? Let's investigate. If we have a segment length of 7, and then you would put 4 and 4 from each end, that makes a nice isosceles triangle. If you started with 7 for the bottom and you used just 3 and 3, notice that those would not reach. Even if you put them down basically flat, 3 and 3 is only 6. So there would be a space of 1 in between there. The ends for those last 2 sides would not meet. So what relationship do we need to have? Remember, we're on inequalities. So how do those measurements have to compare? Well, if you add up 2 sides of a triangle, they would have to add to be more than the other side. Otherwise, they don't reach. So think about that last example. 4 plus 4 is bigger than 7, so that one worked. 3 plus 3 is not bigger than 7, so it did not reach to make a triangle. So this is called the triangle inequality theorem, and it's true about any 2 sides compared to the other side. So there are 3 inequalities that the theorem needs to be true. There's one that's kind of a key to it, but all 3 are true based upon the theorem. Pause and get your hypothesis and conclusion written down. What's the hypothesis? You need a triangle. So that if you're drawing a picture, the triangle is the hypothesis. Those greater than relationships are the conclusions. So now I'll give you 3 lengths, and let's assume that the units are the same, like 7 inches, 10 inches, 9 inches, or 19 inches, I'm sorry. See whether that will make a triangle. So you need to do the adding. Does 7 plus 10 add to be more than 19? Oh, and right away, nope, that didn't work. So I don't even need to keep trying the others. It's not going to make a triangle because those 2 would not reach if the other side is 19. Try this combination. It did work no matter which 2 you add compared to the other. So yes, this will make a triangle. All right, in this problem I didn't directly give you the lengths, so your first step is to substitute the n in and calculate what each length would be, then do the adding idea to make sure that 2 sides are more than the 3rd side. Go ahead. Then when you compare, it does work. How about 8, 13, and 21? Well, you might notice that 8 plus 13 is equal to 21. So does that work to make a triangle or not? It does not. The relationship, we needed to be a greater than relationship. So if you were trying to draw this, it would be completely flat, like a collinear, just a line, where the length of 8 and 13 exactly equals 21. So no triangle would be formed. Substitute, and then examine the lengths. It did form a triangle. Now this is a little bit different type of problem. I'm giving you 2 side lengths, 8 and 13, and you have to give me the range for the 3rd side. Like how short could that 3rd side be? How long could it be? You might think from that last problem, or a problem we did just not too long ago, the 8 and 13 add to be 21. But it's not going to make a triangle if that third side is exactly 21 because it would be flat. So you have to have that third side to be shorter than 21, otherwise they won't reach. But how short could it get? Okay, here's doing all the inequalities. So I would get that the length has to be greater than 5 inches and less than 21. I'm going to back up and try and draw this out and explain it a little bit different way than what you see there. If we had the triangle, let's say the 8 and the 13 were really far apart. So this last side had to be less than 21, otherwise it wouldn't reach. Now the other way that you can do the 8 and the 13 is, let's say this is 13 and we've turned the 8 so that it's really almost flat with it. So it's going to make a different triangle than the first example. How long would this side be? Well, it would be flat if it were 5. So does it need to be more than 5 or less than 5 to make a triangle? Notice the side would have to be more than 5 in order to get 8 plus that number to be more than 13. So putting these two ideas together, I got that the side has to be bigger than 5. 5 is less than the side is bigger than 5, but the side had to be less than 21. So I'm getting the range of 5 and from 5 to 21 is how long that third side could be. Here was the textbook type of explanation. So see what you can do with this next one. I think what I skipped there, this is what I flipped back and did. Okay, you try 23 and 17 for the side lengths. What's the range of possible lengths for the third side? You've got to pause it and try it, and then check your answer. Okay, the range would be from 6 to 40. If you want to do the picture that I did before, if you had the 17 and the 23, the long length would be 40. It can't be that long, so the side had to be smaller than 40. And then 23, if the 17 was pretty flat to it, this last side would be again related to 6. It would have to be bigger than 6, otherwise it wouldn't make a triangle. So I still get, it has to be greater than 6, but less than 40 at the same time. Relating it to a map, read the information and answer the example. Pause. Did you get between 5 and 97? Maybe you've noticed that to get the two numbers in the range, you actually subtract the lengths and add the lengths to get the lower and upper bound of this range. So keep that in mind as you do this one, you'll be faster. You should have come up with greater than 28 miles, but less than 72 miles. Okay, check of understanding. Try these two problems and then check your answers. Pause. Okay, the answers. Did you get them right? Here's some more that we did in this section. coming up with those answers. All right, so that was dealing with one triangle and some inequalities. Now we're going to go to the 5-6 section and compare two triangles, and there's some inequality relationship. Okay, I want you to think about a doorway, because this theorem is going to be called the hinge theorem. If you think about opening and closing the door, that might help you really understand why the hinge theorem is called what it is. It says when you open a door, the walkway can be narrow or wide depending upon the angle formed between the door and the door frame. The door and the door frame would be like two sides of a triangle, and then you're opening and closing the angle that's in between, kind of like side angle side. Think of the door, walkway, and door frame forming the triangle like I just described, and the angle formed affects the width of the walkway. If it's open wider, you've got a bigger walkway to come in. That's the idea of the hinge theorem and its converse. You'll need to pause this. If two sides of one triangle are congruent to two sides of another triangle. So that's what's making our hinge. So as you look at the diagram, you've got AB and DE the same. You've got AC and DF the same when you compare the two triangles. That is the hinge. How wide is that open? Well, it says that angle A is open wider than angle D. So that can tell us that the opening BC is going to be wider than the opening EF. Think about the door. When you're going through, the opening is open wider. You've got a bigger walkway to walk through. Now the converse begins with the side lengths making the hinge, and then they're comparing the remaining two sides. It says that GH is longer than KL. So then in the conclusion, that would mean this hinge for angle J is open wider than the hinge for angle M. So again, it's not an equal relationship. They're comparing to see which situation is greater, which is less. Okay, so you need to look for the hinge. What segments in the two triangles make the hinge? And before I show the solution, I'm going to mark, let's see, we had 4 and 4, and then we've got this reflexive side. So the top triangle has these two sides congruent. The bottom triangle has those two sides in those positions. Now, what other information are we given? Well, the last side in the top triangle is 7. The last side in the bottom one is 6. So the hinge on the top triangle is open wider than the hinge on the bottom one. So the angle in the top one is bigger than the angle in the bottom one. So compare angle BAC. We're going to say BAC is greater than angle DAC because the hinge is open wider. Here's the written out solution to that. We're using the converse of the hinge theorem because it didn't give us the size of the angle hinge. It gave us the length of the third side in the triangle. Okay, for this one, try and find the hinge, the sevens, and then the reflexive side. So the hinge on the left is open at an 82-degree angle. The same hinge on the right would be open at, what's 180 minus 82? That was 98. So that hinge on the right is open wider. So that's going to tell me FG is longer. So to answer the question, comparing EF and GF, EF is going to be less than GF because the hinge is not open as wide on the left side as it is on the right side. Okay, just like we did a range of values in that one triangle situation, now we've got a range of values in two triangles related to the hinge theorem. So let's first think through, like we've been doing, the hinge, again, is this segment and the reflexive one, the top segment and that reflexive one. This length is longer than 18, so that would mean this bottom angle, the 38-degree angle, is larger than the angle in the top triangle. Okay, so wouldn't that give me a relationship that the 38 is greater than 5k minus 12? Maybe you wrote 5k minus 12 is less than 38. That's the same thing. I probably would have preferred the other way around, but we do get k is smaller than 10. That said a range, so it's smaller than 10. How small could it get? Well, if we have this angle 5k minus 12, for it to be small but remain an angle, wouldn't it have to be more than 0 degrees? So that's the other part of our range, is we know it's small, but we can't let it get too small or there won't be an angle. So to continue on, the 5k minus 12 has to be greater than 0. Add 12, divide by 5. Remember when you solve inequalities, if you're dividing by a negative or multiplying by a negative, you have to reverse the inequality. Otherwise, it's just like doing equations that have equals. So our range here, that k, the length, or the value of k could get as small as positive 2.4, but can't get any bigger than 10. Has to be in between that range. So the 0 part is what you need to come up with after you have compared using the hinge theorem. So try this one. You're trying to figure out just how the angles compare. I guess this is not a range one. This is just back to your which one's greater, which is smaller. So pause and try it. Well, kind of did that too fast. Okay, so the EGH would be smaller. EGH. This angle would be smaller than this one because the side across from it is shorter. The hinge is not open as wide. Next example. BC is going to be larger. Here's a range of values problem. Okay, look for the hinge. This side and then the reflexive side. Open at 120 degrees. The same segments here, open at 90 degrees. So set up your less than or greater than. Could be done either way. You just have to solve what you set up correctly. Then you have to think of the 0 part. Okay, I quickly wrote that that was 7. So what steps did I do? I probably would have subtracted 23. Actually, I probably would not have started with that. Let me go back. I think I would have subtracted z. To get 2z plus 9 is less than 23. Then subtract 9 and divide. I'm only dividing by a positive 2, so I don't have to reverse the inequality. Okay, so that's where I got the z is less than 7. Now, which of those is the smaller segment? Isn't the 3z plus 9 the small segment out of those two? So we can't let 3z plus 9 get too small. So you're going to say that that has to be greater than 0. So subtract 9 and divide by 3. So you get the range from -3 to +7. Okay, check of understanding for the second part of this lesson. Pause and work both problems. And that's it for today's lesson. Inequalities in triangles.